Hello everyone, welcome to Proton NMR lecture. Not quite the way I was envisioning giving this lecture, but we can make it work. So, we are going to be talking about proton/hydrogen NMR today. So remember that NMR stands for nuclear magnetic resonance. So just like C13 NMR, right, we're looking at the nucleus of the atom, and in order for it to spin flip, then it needs to absorb certain frequencies of radiation, of energy, and that is down in the radio wave frequency end of the electromagnetic spectrum. So not very high energy. And again, we're going to look at proton. I call it proton NMR. You will see it written as H1 NMR. You can call it hydrogen NMR. It all means the same thing. The reason that we tend to call hydrogen NMR proton NMR is because when you think about a hydrogen atom, I'm looking at a periodic table, but when you think about a hydrogen atom, what's in its nucleus, right? And what's in its nucleus, it has one electron and one proton and no neutrons. And so it just has one proton in its nucleus, and since we're looking at nuclear magnetic resonance, essentially we are looking at a proton and how that proton is responding. And so again, hydrogen NMR, proton NMR, same thing. But before we get to hydrogen NMR, let's start with carbon NMR, which is the picture that you see behind me. You have all of these pictures in your manual. I forgot to bring a manual down the hallway with me, so you'll have to sort of flip through that yourself. But you have all of them in the very beginning of your manual, so you should be able to find them. So just as a refresher for carbon NMR, when we look at a carbon NMR really we use them for two things. First of all, we look at the chemical shift of the peak, and that will tell us something about what type of carbon it is. For example, this carbon is this peak is way out here in the 180, 178 area, and so I would instantly call that a carbonyl carbon, right? So our aldehyde and ketone carbons are down here, our carbonyl carbons are here, our double bond and aromatic carbons about 110 to 160, 170, somewhere in there. Sort of 80 to 100, you might find your triple bond carbons. And then this I would probably identify as a carbon singly bound to an oxygen. So we have our carbon oxygens here. And then you kind of have a mishmash of things, right? So probably, anywhere in here you have carbons bound to nitrogens and carbons bound to halogens. And most upfield, remember downfield, upfield, most upfield would be our alkane-like carbons. Remember, TMS is an external, we call it an internal standard. We physically add it to the NMR tube so that we can tell the instrument to set that peak to 0 ppm. Right, so TMS is our standard for carbon as well as for proton. So remember, carbon we get single peaks, and the chemical shift can give us an indication of what type of carbon that might be. The other piece of information we get from a carbon spectrum is simply how many peaks do we see. And so for this molecule, we see 1, 2, 3, 4 peaks. And so we would know that there are 4 different types of carbons in this molecule, right? So then we would look at the molecular formula. And if the molecular formula tells us that there are 8 carbons in the molecule and we see 4, then we would know there's complete symmetry. And if the molecular formula says that there's 6 carbons and we see 4, that would tell us that 2 of those carbons are the same. So there's sort of little bits of symmetry, and they're not completely symmetrical, but not completely unsymmetrical. And so if you look at your molecular formula and there's 6 carbons and there are 4 carbons and you see 4 peaks, then you know you have no symmetry in your molecule. Right, so those were the two things, symmetry and chemical shift. That's what we really were looking at C13 NMR for. So as practice, hopefully see these two molecules. Why don't you go ahead and tell me how many carbon peaks you would expect to see for each one of these molecules. So you can go ahead and pause the video now so that you can see the two molecules, and then figure out how many different carbon peaks you would expect to see in the spectrum of those molecules. All right, so unpause when you're done, and so presumably you have unpaused yourself. Ideally, you said that the correct answer here was 8. Eight carbons, so 1, 2, 3, 4, 5, 6, 7, 8. That one is the same as that one. That one is the same as that one, and these two are the same. Right, so remember your symmetry. Then when you go to the second one, this one is a little bit, not tricky, but you had to remember one thing. And the correct answer here is that there are actually going to be 9 different carbon peaks. And so there's a little bit of symmetry through this ring. So this carbon is the same as this carbon. And that carbon is the same as that carbon. But then all of the other carbons are different. And so you have to be a little bit careful and recognize that this carbon is different from that carbon, right? So these two methyl groups are different from each other because this double bond restricts any kind of rotation. And so that means that this methyl group is always going to be cis to an R group. This methyl group is always going to be cis to the hydrogen. And that makes the environment around those two carbons different from each other, different enough that they will show up as different peaks. So 1, 2, 3, 4, 5, 6, 7, 8, 9 different carbons in this molecule. All right, that was your C13 refresher. Then you may remember that we also did depth NMR. And when we think about depth NMR, depth again is a C13 NMR experiment, so we're still looking at carbons. This down here was the carbon spectrum of this molecule, ipsenol. And then there's a 45, which again shows all carbons except quaternary carbons. So carbons that don't have any hydrogens don't show up. And then we had a depth 90, and remember in a depth 90, the only types of carbons that we see are carbons with 1 hydrogen on them. So in this case, there are 3. And then in the depth 135, in the positive direction, you see carbons with 1 hydrogen and carbons with 3 hydrogens. So in this case, we see 1, 2, 3, 4. And if we compare it to knowing that there's 3 CH groups, that means there's 1 CH3 group. And then the ones that go below the axis are CH2 groups. So we know we have 1, 2, 3, 4. And again, in any of the depths, the carbons that you don't see, you will never see in a depth spectrum, are the carbons that have no hydrogens bound to them, so the quaternary carbons. All right, so that is a review of what we did last semester. So let's go ahead and start talking about proton NMR. So we're going to start with proton NMR, and you have this sheet. There are 8 compounds. Go ahead and pause the video now, and what I want you to do is to just tell me how many equivalent protons or hydrogens are present in these molecules. Right, so just like carbon, right, this one I can reach, so I'm going to talk about it here. Right, you would imagine there's a plane of symmetry through here, So you would tell me that these two carbons are the same. And if those two carbons are the same, then the hydrogens bound to this carbon and the hydrogens bound to that carbon must be the same. And so in this case, I would say that there is one type of hydrogen or one type of proton that I would see in this molecule, which happens to be acetone. So go ahead and pause the video and tell me for the rest of these how many different types of hydrogen peaks you would expect to see in the proton NMR. Okay, so the answer is, because I know you're back now, the answer is that for this molecule, bring it down to my height, right, this molecule has two planes of symmetry. And so it turns out these hydrogens and these hydrogens and these hydrogens and these hydrogens are all the same. So you would have one kind of hydrogen for this molecule. And over here, right, you have methyl iodide. These three hydrogens are all on the same carbon, so they're equivalent to each other, which means that there's only one type of hydrogen. And we did acetone because of the symmetry. Those hydrogens are the same as those, so there's one type. And then here we have our beloved molecule benzene, which has hundreds of different planes of symmetry. And because of that, the hydrogen here and here and here and here and here and here are all equivalent to each other. So again, I'd have one type of hydrogen for this molecule. So now when we look at this, right, so there's not really a whole lot of symmetry here in this molecule, but what you should recognize is that that carbon and that carbon and that carbon are all equivalent to each other. And if the carbons are equivalent, then the hydrogens on them are equivalent. And so therefore, these hydrogens are the same as these hydrogens are the same as those hydrogens, but they're different from these hydrogens, right? So in this case, I would see two different types of hydrogens in this molecule. I would see these, and I would see these. So remember, when I'm saying types of hydrogens, I'm not talking about is it a CH3 or a CH2 or a CH, right? I'm talking about in the molecule that you are looking at, are they equivalent to each other? And these hydrogens are very different, right? This methyl group is very different from these. All right, so over here for number 6, we have two planes of symmetry. We have a plane of symmetry that runs right down through there. We have a plane of symmetry that runs right through the center. And so because of this plane of symmetry, that hydrogen is the same as that hydrogen. And that hydrogen is the same as that hydrogen. Because of this plane of symmetry, that hydrogen is the same as that hydrogen. And if that hydrogen is the same as that hydrogen, and that hydrogen is the same as that, right, blah, blah, blah. So you can see that these 4 hydrogens are all the same. And these two methyl groups, if I fold along the center of this molecule, that methyl and that methyl are the same. So for this molecule, I would have anticipated 2 different types of hydrogens. Down here, okay, so we do not have symmetry there. We do not have symmetry there. We don't have any kind of symmetry. And so I would say that we would see 1 type of hydrogen, 2, 3, and 4 different types of hydrogens. Remember, these 2 aren't the same for the same reason the 2 methyl groups in example 2 that I gave you, those 2 methyl groups are not the same. This hydrogen is always going to be cis to this methyl group. This hydrogen is always going to be cis to a hydrogen. So that makes these 2 different. Similar, but different. So this would be 4. And then over here, plane of symmetry through there, same, but these 2 are different from each other, so the correct answer here would be 2 types of hydrogens. Okay, it's been a long time since I had to talk this long. So, then think I gave you just a whole variety of examples. So here's the first example that we did. You can see, and for now you can ignore, this is actually a thin line that is doing that. You can ignore that piece and that piece, but you can just see there's one peak. Let me talk about chemical shift for a minute, because remember, for a carbon spectrum, we tended to look from 0 to 200 ppms, right? So that was a really long, wide spectrum. For proton NMR, we tend to really look from 0 to 10, maybe 0 to 12, right? Depending on what we're looking for, right? But it's a much more condensed chemical shift. So because of that, you're going to have a lot more overlap of protons. And really where you're going to see the overlap is sort of in this region. So you're going to notice that from, maybe 1.5 to 3, you're going to have a fair amount of overlap. And so you pay attention to chemical shift, but it's not necessarily going to give you the kind of information it might give you in a carbon spectrum. But in this case, you can see the methyl group. There's one type of hydrogen. And then we did methyl iodide. Again, one type of hydrogen, same general area. Then acetone, one type of hydrogen, around 2. And then down here we had an example of methanol, deuterated methanol. And I have to flip a couple pages. Right, when you look at benzene, again, there's one peak, but what you'll notice is that it's very far downfield from the peaks that you've been looking at. The peaks you've been looking at before have all been in here. Now you're going to get a peak down here, and so you will learn that the chemical shift area for aromatic hydrogens is generally between 7 and 8. But we'll get there. I think this was an example that we did, right? All of these methyl groups are the same, different from this methyl group, and so what you see here is you see 2 peaks. And you can probably imagine that these hydrogens bound to a carbon, bound to an oxygen. Oxygen sort of pulls things downfield, so these are going to be that one. And this peak upfield is alkane-like hydrogens, and those are alkane-like hydrogens. And then we did the example of paraxylene, to start using some of our words again. And so you can see, remember we said these 2 methyl groups were the same, and they are about down here, and that these 4 hydrogens, and we already know that aromatic hydrogens are pulled downfield, so these 4 hydrogens are represented by that peak. And then the last example we looked at was diethyl ether, which we said had 2 different kinds of hydrogens, and you see 2 different kinds of hydrogens in the spectrum. So, so chemical shift. Okay. So there are 3 things that proton NMR can tell us. One of them is chemical shift, right? It's easy just to look at what the chemical shift on your, of your peaks is. Let me try to see if I can move this over here for you to see. Right, so there are 3 things that we will eventually talk about. One of them is chemical shift. One of them is integration. And probably the most important one is called splitting patterns. Okay, and we'll discuss all three of these today. But chemical shift for proton NMR is really very similar to chemical shift for carbon NMR, right? Again, it's something that you have to become familiar with. Don't memorize the numbers, but do become familiar with them. And so I've tried to, there's lots of information on the sheet. I've tried to show you what I think the important ones are for you to remember. First of all, TMS, right? TMS is going to be 0. It's 0 in carbon, it's 0 in proton. That's why we use that molecule. You can see your alkanes, and this is really where I want you to be careful. I know that they say CH3 and CH2 and CH, and they've given 3 different values, but you can see these values are basically all upfield. And so what I want you to remember is that alkane-like hydrogens, hydrogens that are in carbons that are simply bound to other carbons, right? Those alkane-like hydrogens are upfield, anywhere from really 1 to 2, but, they're the most upfield peaks you're going to find. And so that's what I want you to remember, not these exact values, because of course these are all ranges. Alkenes, right? So when you have an alkene, when you have a double bond, and you have a hydrogen bound to one of those carbons, right? So I have a hydrogen on a carbon, and that carbon is part of a double bond. That alkene-like, it's not alkene-like, it is an alkene hydrogen. Sometimes you'll hear us call it vinyl. But that alkene hydrogen is going to show up 4.5 to 6, right? That's a pretty distinctive area. So oftentimes if you see a peak between 4.5 and a 6, you tend to think, oh, maybe I have a double bond in there. Down here you see aromatic, right? So those aromatic hydrogens, this is a pretty wide range, 6 to 8.5. The truth is, usually aromatic protons show up between 7 and 8, right? And again, these are approximate ranges. They can go down to 6, and it can go up to 8.5, but generally speaking, you will see your aromatic hydrogens between 7 and 8 ppm. Then you can ignore the ones underneath it, because there's just lots of overlap. And then we'll come over here. Okay? So if you have a hydrogen, and this is where you have to be careful. These are our ethers and our alcohols. Really, our esters fall into this category too. You can see right here, it's the same category. If you have a hydrogen, because remember, we are looking at hydrogens. This hydrogen is bound to a carbon, and that carbon is bound to an oxygen. That oxygen causes this hydrogen, to move downfield. And that area where those hydrogens usually show up is between 3.5 and 4. And so if you see a peak pull down to 3.5 and 4, you should start thinking, maybe that's a hydrogen that's bound to a carbon that's bound to an oxygen. Okay, same thing here. This is an ester, but hydrogen bound to a carbon bound to an oxygen, same region, 3.5 to 4. So there's only 2 more that are distinctive. One of them is your carboxylic acid, right? If you have a hydrogen bound to the oxygen, remember that's a carboxylic acid, so go back and review your functional groups. But the hydrogen of a carboxylic acid tends to show up between 10 and 12. It's the peak that is furthest downfield, right? So 10 to 12. And then the other peak that's downfield, just not quite as far, is your aldehyde. So remember that is an aldehyde. And the aldehyde hydrogen is distinctive because it shows up between 9 and 10. And so when you think about, find a black pen, when you think about your carbon spectrum, or not your carbon spectrum, your hydrogen spectrum, bring you back over here. Right, if this is TMS at 0, you have your alkane-like hydrogens here, maybe around 3.5. You start having hydrogens that are bound to a carbon, that are bound to an oxygen, 3.5, and then maybe about, I don't know, 4.5 to 6. That's where you have your hydrogens that are part of a double bond. And then you have your aromatic hydrogens. And then, right, from 9 to 10, you have your aldehyde hydrogens. And then from 10 to 12, you have your carboxylic acid hydrogens. Okay. So they're not nearly as many, or they don't seem to be, in my mind, nearly as many chemical shifts to remember because lots of things really overlap in that region. All right, so that is the discussion of chemical shift. Before we move into the idea of integration, why don't you pause the video and take a 2-minute break. Of course, I'm not pausing the video. Welcome back. So what we're going to talk about now is the idea of integration. And integration is not something that we did with carbon NMR, right? So yes, chemical shift is similar between carbon and hydrogen, but the next two ideas, very different, right? And that's often why between integration and splitting pattern, that is often why a proton NMR is, sort of the go-to for organic chemists, right? Because we can actually get so much more information from it. So let's talk about integration. Basically, what integration is telling you is how many hydrogens are represented by a peak. And so when you look at this spectrum, it's ethyl acetate. Until we get to splitting pattern, right now, I want you to just think of, well, I mean, even in the future, I want you to think of this. I know it's not one peak, but it is one grouping of peaks, and so it's one type of hydrogen. And this is one peak, but it's also one type of hydrogen that's different from that. And again, this is not one single peak, but it is one clump of peaks. It is one type of hydrogen. So if I were to look at this spectrum, it looks like to me that there are 3 different types or 3 different kinds of hydrogens present here. I see one here, and one here. And so when you integrate a peak, what I'm curious to know is I know that this is one type of hydrogen, but is it truly one hydrogen or 2 hydrogens or 3 hydrogens, right? And I can't tell that from just looking at the peaks. But I can tell that if I integrate the peaks. And so by integrating your spectrum, what you are going to be able to determine is the number of hydrogens represented by each one of these groups of peaks. And so you just tell the computer to do this integration. And in fact, our instrument, you're going to tell the computer to integrate like this, right? So it just integrates each group. And really what the computer is doing is simply measuring the area underneath each one of these individual little peaks. Right? It's measuring that area and equating it to, in this case, a line. And it measures the area under that group of peaks, it measures the area under that peak, and it measures the area under this peak, and it spits out a ratio. And that number that you get is just a ratio of that area compared to that area compared to that area. And so you can see for this spectrum, it's telling you that this grouping of peaks integrates to 2, and this integrates to 3, and this integrates, again, you're going to round this up, that integrates to 3, right? So that's what the integration is telling you. It's telling you that this represents 2 hydrogens. I know that this is a CH2, and this is a CH3, and this is also a CH3, right? And I know that because that's what the integration is telling me. The integration is telling me how many hydrogens are represented by that peak. Please remember, so let's go back to one of these other pictures. So you can do the integration yourself if you want, right? That's what this line is. Here it goes up, and here it goes up, and here. So that height from here to here is the area underneath this peak, and then from here to here, right? So that distance is the area underneath this peak. And then the computer just takes that height compared to that height, does a ratio, spits out a number for you. Okay, so it's just a ratio. Now in this case, the computer would have given you a value like 2 and 3. And so that would say to you, this represents 2 hydrogens, and this represents 3 hydrogens. Because the computer is just giving you a ratio, it doesn't know what your molecule is. So you have to use your chemical senses and understand that because I know what the structure of this molecule is, because of the symmetry of this molecule, and because of the chemical shift, I know that these 2 hydrogens are the aromatic hydrogens. But I really have 4 aromatic hydrogens, right? So really this 2 to 3 ratio, because I know my molecule, is truly a 4 to 6 ratio, right? Because 2 to 3, we're multiplying both by 2, you'd get 4 and 6. Right? So you have to use integration with a little bit of sense. Either you know what your molecule is, in many cases you don't know your molecule, but you might know the molecular formula. And if the molecular formula you're given was C8H10, if you know there are 10 hydrogens, but it only integrates to 2 and 3, so it only integrates to 5, then you know that really each one of these is double. Okay? Also, if you get you shouldn't, but if you ever get a ratio of 1 to 1.5, you have to use your chemistry spidey senses and recognize that 1.5, you can't have a half a hydrogen. And so instead of 1 to 1.5, that's really 2 to 3, or 4 to 6, or 6 to 9. Let me make sure I did my math right. Right? So it's just a ratio. But integration is important because of what it tells you. And it tells you how many protons are represented by that peak. All right. That is integration. Let's now talk about the very last idea of proton NMR, and that is splitting patterns. So, if you look at this molecule, it's ethyl bromide. I would hope that you could tell me that these 2 hydrogens are different from these 3 hydrogens, so that you would expect to see 2 different kinds of hydrogens in the spectrum. And in fact, you see 2 different kinds, right? You see one kind here and one kind here. And hopefully, if I made you, without knowing anything else, if I made you guess which one of these was which, hopefully you would say, well, these 2 hydrogens are bound to a carbon that's bound to a heteroatom, and that tends to pull things downfield. So I'm going to guess that these hydrogens are these 2, and that these upfield alkane-like hydrogens are those. And I would say you're absolutely correct. And then if you had propyl bromide, hopefully again you would say 1, 2, 3 different types of hydrogens. 1, 2, 3 different types of hydrogens. I would guess that this one pulled furthest downfield are probably these 2. These hydrogens that are mostly alkane-like are here. And this one in the middle are the hydrogens here in the middle. Again, you'd be correct. Then isopropyl bromide, because of the symmetry, these 2 are the same, different from the hydrogen here. So 2 types of hydrogen, one here, one here. All right, so that is just looking at the hydrogens and how many you expect to see. But now what I want you to do is to look closely at the spectra on here and actually count how many peaks you see in this grouping. How many peaks do you see in this grouping? Right, go through there on this whole sheet and try to tell me how many peaks you see. So pause it and do that. So come back. So I would say that, it's hard for me to see here, but if you look closely, you should see that there are 4 peaks here, and that there are 3 peaks here, and that there are 3 peaks here, and maybe around 6 or so in here, and 3 peaks here. And then in the bottom spectrum, you should see 2 here and 7 here. And so the question becomes, where does that come from, right? Why are some 2 and 7 and 6 and 3 and 4 and 1 and right? Where does that all come from? Well, that comes from a very specific place, and that what the pattern is is really the idea behind splitting patterns. So before we talk about where splitting patterns come from, I want to actually talk about what they look like. And in fact, you have this piece of paper, so you can pull it out. But I'm going to draw them here for you. So if I see something that has two peaks, right, and I'm sorry, they're supposed to be two similar peaks, right, but two peaks that are close to each other like this, right, I'm going to call that a doublet. And I'm going to represent that with a D. And then I should have started with, if you see one peak, we call that a singlet, and we represent that with an S. So a singlet is one peak, a doublet is two similarly sized peaks right next to each other. A triplet is three peaks, but they're really in a ratio, an approximate ratio of 1 to 2 to 1. Right, so that would make it a triplet. And we represent a triplet with a T. The next pattern you would see is a 1, 1 to 1, 1, 1, 1, which is a quartet. And a quartet is really, it's four peaks, but they're in a ratio of 1 to 3 to 3 to 1. Right, so that's a quartet. And we represent a quartet with a Q. And virtually everything else we simply call a multiplet. And we represent a multiplet with an M. And that, you know, usually as I said before, you get a lot of overlapping in proton NMR. And when two things, even if one of them's a quartet and one of them's a doublet, if they overlap each other, you can't really determine what they are because they have sort of a mixed up pattern. And when that happens, we just simply say multiplet, right? It's hard to get that kind of information. If you take advanced organic, we look deeply into those multiplets and pull out the valuable information. But for right now, we're simply going to be happy to call them multiplets. Okay? So really, singlet, doublet, triplet, quartet, and multiplet, that's what we're looking at. There is something called a J value. And a J value is the same thing. Looks like my pen is leaving me. It's the same thing as a coupling constant. And J values are something that you can measure from your NMR spectrum. But essentially what that is saying and why that is valuable is that if you're trying to determine, is the peak I'm looking at a triplet or is it something else, right? The way you can determine that is by looking at the distance between these two peaks, right? So these two peaks. That distance needs to be the same as that distance, right? So the distance here and the distance here have to be the same. And if they're the same, right, that's your J value, whatever value that is. If that's your J value, if they're the same, then you can legitimately call this a triplet, and it's not going to be overlapping peaks, right? Same thing here with your quartet. That distance to that distance to that distance, if those three values are the same, that's a J value. that's a quartet, right? So we, again, we in Organic 1, Organic 2, are not going to look at J values. We're not even going to worry about what they mean, but just know that they help you recognize whether peaks are overlapping or whether they are truly a quartet or a triplet or a doublet. Okay? So those are our J values. So how do I know? How do I know if my hydrogens are going to be a triplet or a quartet or a multiplet? You know, how do I know? Well, you know because of something called the N+1 rule. So I'm going to write the N+1 rule on the board. Try to move you over here. So the N+1 rule. Try to find a darker pen. So the N+1 rule. The signal of a proton that has n equivalent neighboring protons is split into a multiplet of n+1 peaks with constant coupling. With constant coupling, J values. You know, for now I'm going to erase that because really that's not going to become important to us. But what is important to us is n+1 and n equivalent neighboring, and I'm going to highlight neighboring protons. Okay. Integration tells you how many protons are in one peak. The splitting pattern, what pattern I am, is not dependent upon how many protons I am. It's dependent upon how many neighbors I have, right? And so interpreting splitting patterns is what helps us build molecules, because I can identify one type of proton, and then I can identify what splits it, so now I know the neighbor, and then I go to that and I determine its neighbor, and I go on, and so I can start to really build my molecule based upon my splitting patterns. That's why they're really important. And I'm going to say right now that the area where people get confused is mixing up n equivalent neighbors with integration. Right? Integration tells me you are two hydrogens. If I'm split into a singlet, that means that I have 0 neighbors, right? So when you think about your patterns, right, n is the number of equivalent, right, they have to be the same, equivalent neighbors, and then I get split into n+1 peaks. So let's go back to this page. Right, you have your ethyl bromide. So, if I am these two hydrogens, I am going to integrate to 2. Right? I'm going to integrate to 2 because I'm a CH2 group. But what is my splitting pattern going to be? My splitting pattern has nothing to do with me and only has to do with my neighbors. So, well, here I don't have any hydrogen neighbors, so I don't have to worry about it. Right? But here, obviously I have a carbon. This carbon has 3 hydrogens on it. So, if I'm these hydrogens, the number of equivalent neighbors that I have, equivalent to themselves, is 3. I have 3 neighbors. And so that means N equals 3. My splitting pattern is N plus 1. So if I have 3 neighbors, N plus 1 would give me 4. So that means that I would be split into a quartet, right? N plus 1. So I integrate to 2. My splitting pattern is a quartet. Now let's do these hydrogens. Integration, I integrate to 3. I'm going to integrate to 3 hydrogens. Whenever I see 3 hydrogens in an integration, I instantly say, oh, that's a methyl group. Excuse me, that's a methyl group, right? Because that's you know by now, that's a very common group in organic structures. So, here I am, I integrate to 3. What is my splitting pattern? My splitting pattern is based on my neighbors. So I have 2 hydrogens here. I have 2 neighbors. So N is 2. So my splitting pattern, N plus 1, would be 3. So I would be split into a triplet. Come over here, you see a triplet. Let's look at the one underneath it. Again, integration is 2. How many hydrogen neighbors, right? Go to this I don't have any neighbors on that side. Go to this carbon. How many hydrogens are on this carbon? 2. Remember, we're not going multiple out. We're just going to one carbon. Go to the neighboring carbon. This carbon has 2 hydrogens on it. So for me, N would be 2. So N plus 1 would be 3. So I would show up as a triplet. If I'm these hydrogens, I have 2 neighbors, I would show up as a triplet. Here's where the interesting stuff comes in. Now I'm going to be these center 2 hydrogens. Okay. Over here, I have 3 hydrogen neighbors. Over here, I have 2 hydrogen neighbors. So I have 3 on this side of me and 2 on this side of me. Right? You know that these 3 hydrogens are different from these 2 hydrogens. And because they're different from each other, you can't simply say 3 plus 2 gives me 5, N plus 1 gives me 6, I will be split into 6. Right? It's not that simple. It might be how that looks, but it's certainly not that simple. Okay? And so that's when you have to go back and look. I walk over here, but I realize the camera doesn't follow me. That's when you go back and look at your N plus 1 rule that says that in order to have a value of N, they have to be equivalent neighbors, right? And these hydrogens are not equivalent to these hydrogens, so we can't just add them together, all right? And that's when we see multiplets, So this I would define as a multiplet. This I was defined as a multiplet. There's no really nice pattern in here. It's clearly overlapping of things. For those of you who want to know, again, not holding you to this for organic 2, but what happens to these 2 hydrogens is that these 3 hydrogens split them according to the n+1 rule, right? So these split them into a quartet, and these 2 split them into a triplet. And so what you really get is a triplet of quartets, which would really give you 12 peaks. But those peaks all start to overlap each other, so that's why you don't see actually 12 peaks. So we're not going to worry about that being a triplet of quartets. We're just going to call it a multiplet. Now you look at the last one. We have 1 hydrogen here, but in this case, these 2 methyl groups are the same. So if I'm this 1 hydrogen right here, and I look at my neighbors, I have 3 neighbors there and 3 neighbors there, and this time those neighbors are the same. They really are equivalent to each other. So this time, I have n equals 6. 6 plus 1 is 7. My 1 hydrogen, I would be split into a, well, we would call it a septet. Okay? And you can see that this pattern is really much nicer than this pattern, right? This pattern is a multiplet. We have tall peaks and little peaks, and nothing that really looks like a nice pattern. This clearly looks like a nice pattern, and so you could call it a multiplet. If you look at it closely, you can see it's a septet. You can see that it's going to make sense. If you see a septet, start to think, oh, that was 6 hydrogens that are equivalent. That's 2 methyl groups. That might be an isopropyl. But anyway, even if you call this a multiplet, that's fine. When I look at this peak, right, these 2 methyl groups are the same, but they are split by this 1 hydrogen here, right? This has 1 neighbor. And if I have 1 neighbor, n equals 1, then n plus 1 equals 2 makes me a doublet. So these methyl groups show up as a doublet, 2 equivalent peaks. So I have a doublet if I have 1 neighbor. I'm a triplet if I have 2 neighbors. I'm a quartet if I have 3 neighbors. I'm a multiplet if I have really anything more than that. And I'm a singlet if I have no neighbors. So just for an example, I'll go ahead and do an example. I seem to have lost my pen somewhere. Guess I'll have to use this big fat pen. There we go. Right. So if I look at this molecule, I just want to give you an example of a singlet. Right? These 2 are the same. I'm just rolling out this carbon here. These hydrogens I go to this oxygen, I don't have any hydrogens on that oxygen. So I have 0 neighbors, and so these hydrogens will show up as a singlet because 0 plus 1 gives me 1, which